So for a while now we have been discussing serial links with equalization. We can have the equalization at the transmitter or the receiver. If you have a very complicated equalization at the transmitter, the amplitude can be limited, and also it's harder to adapt because the output of the equalizer plus channel is at a different place than the equalizer itself. Or you can have equalizer at the receiver, in which case you can also do the adaptation. We saw algorithm to do that. The LMS adaptation does it very well. Now, so far we have been considering linear equalizers, and the disadvantage with the linear equalizer is that it tends to amplify the noise. So it's easiest to see when the equalizer is at the receiver. So if some noise is added into the channel, let's say noise or crosstalk, then the equalizer provides a boost at high frequencies, which also ends up boosting either noise or crosstalk. So in case of crosstalk, the crosstalk itself tends to be high at high frequencies. So you're providing gain exactly at the frequencies where the crosstalk is highest. Okay, so that is a problem. So what we do now is to see if there is some kind of equalization that we can do, in which case we don't have to boost. We end up not boosting the noise. Is it possible? Is it possible to do equalization without boosting noise? That is, I am imagining a scenario where I have the transmitter, then the channel, then I have either this could be noise or this could be crosstalk, and I have the receiver. So if it is noise, it could be random, uncorrelated to the signal, and if it is crosstalk, it's reasonable to assume that it comes from a similar kind of transmitter. Not that it's transmitting the same set of bits, but it comes from, if you assume that the output levels of this transmitter or something, it's reasonable to assume that the crosstalk transmitter also has the same amplitude, same statistics of data. And so let's say we don't know what the noise is. That is the problem, right? Echo cancellation, we know what was the echo. That is the transmitted signal. So in this case, let's imagine a case where we don't know exactly what the noise is or what the crosstalk is. So it is possible. I mean, you can imagine a case, and this is very much reality. So if you have multiple transmitters on the same chip, and then let's also assume, let me have two transmitters and two receivers. Receive 0 and 1. Okay. Now this may introduce some crosstalk into this receiver, but we also have access to the signal. So we can try and cancel out the contribution of this by using an adaptive filter. Okay. So let's assume that that's not the case. We don't know what the crosstalk signal is, or we can just assume uncorrelated noise. Is it possible? Yeah. But the channel attenuation is low pass, so the kind of equalizer response that you want is also high pass. So that's the reason why you have a high frequency boosting filter as an equalizer. So let's say the receiver RH is the equalizer. I do it here. I have a low pass filter. See, we saw earlier that if we rearrange linear filters in any way, we still get the same response, right? So let's say we have a receive equalizer. So we have the transmitter, then the transfer function of the channel, and let's say the transfer function of the crosstalk channel. Okay. So this comes from another transmitter. Okay. So the channel transfer function and crosstalk transfer functions are fixed. You can't meddle around with those things. And you want H channel times H equalizer to be 1, so that you have no ISI in this path. Now it doesn't have to be exactly 1, you can tolerate a little bit of ISI, right? So if the I is a little close, it doesn't matter. So whatever it is, you want a certain, I would say, quality of the channel times the equalizer response. So once this is fixed, right? So let's say this is not 1, this is some alpha, and it could be a function of frequency also. So if you assume this, then the equalizer is a function of the channel, and the transfer function through this path is simply the crosstalk transfer function divided by the channel transfer function. So if you adjust the equalization to be of certain quality, then the amount of boost you have for crosstalk is also fixed. If you have linear filters, this is what happens, and we also know that this is not affected by moving the equalizer to the transmitter, right? So we can have the equalizer here instead of this. Then we have to assume the same kind of transmitter, okay? So we also have the equalizer here. So we get exactly the same output. So we can't do it with linear equalizers. That's what it turns out to be the case. That's what turns out to be the case. So let's see what potentially we can do. No. The equalizer is linear. It's only the adaptation that has some non-linearity in it. Okay. So now here we are imagining a case where the coefficients are all converged to the best possible values. After that, what happens? That's what we are not right now worried about how the coefficients actually go to the right values. Okay. So regardless of any coefficient, you will get the same thing in the I'll call this the through channel and the cross channel. This part is clear? Okay, let's say we have a simple channel which we have discussed many times, and I'll consider the discrete time transfer function of the channel. So the discrete time transfer function of the channel, again, just to remind you, is if you have a discrete time input, you pass it through the transmitter pulse shape, which is frequently a rectangle, but it can be anything else. I mean, the transmitter itself will have some finite bandwidth, so that also has to be accounted for in this. And then the channel, and here you get a continuous time output, and you arrange your sampler so that at the peak of the pulse you sample it. Let's say this is how we define it. This is sampled at Fs, and the output is some discrete time output because of the sampling. So between this and this, we can define a discrete time channel whose transfer function is h of z. So this is what we have been doing all along. I am just showing it again just for emphasis. So let's take a case where h of z is 1 plus alpha z inverse, right? So I send, let's say, binary discrete time bits x of n through the channel h of z, and what do I get here? xn plus alpha x n minus 1. So the previous bit interferes with the current bit. We have assumed a very simple channel where there is interference only from one particular bit, and that is the previously transmitted bit. So this is y of n here, and to get x of n, what do we have to do? So somehow we have to subtract, let's say we had the value of x n minus 1. Somehow, I mean, we know that when we have the equalizer here, we may not have access to it, but let's say we have the value of x n minus 1, then we multiply it by alpha and subtract it from the channel output y of n. So here we get x of n perfectly. Then what do we do normally? So in the receiver we have a decision maker which will resolve it into a digital symbol, right? So notice in this case that y of n has the symbol plus intersymbol interference, and we are subtracting some digital value from it. Okay. So now y of n also has, in addition to this, some noise. So let me not call it n because the index is also n. I'll call it, so let's say w of n, where w of n represents the samples of noise. Okay. So it has intersymbol interference and noise, and w of n could also be crosstalk from some other channel. Now the x of n minus 1 that we are adding is a digital value. So what is the noise here at the input to the slicer? What is the noise component at the input of the slicer? W of n. So whatever noise was there at the channel output appears at the slicer. Now this is different from the case of a linear equalizer where we would have had an equalizer here. So if the channel output has W of n, you will have some other noise W prime of n, which you can expect to be larger than W of n. Okay, because the equalizer provides gain at high frequencies and boosts up high frequency noise. Is this clear? Now the only difficulty is to get this xn minus 1, which we have to subtract. How can we get that? Remember, xn minus 1 is the digital value corresponding to the previous bit. H of z is a channel, yes. We have? Yeah, so if I subtract the intersymbol interfering term, that is like equalization, right? One second. Is the point clear? See, I have xn plus alpha xn minus 1. This is the output of the channel. Okay. Now what is equalization? To get rid of the intersymbol interfering terms as much as possible. Now we can do it using a linear filter where it does some convolution and ends up cancelling the other term, or somehow magically let's say I assume that I have this xn minus 1 and I subtract it. That is also equalization. So essentially, see, this is what appears here is something, let's say the output is y hat of n. Now we assume that for time n minus 1, the decision of the comparator was right. Okay, so that's an assumption for now. So if that's the case, we can delay it by one symbol period. So that means here I get y hat of n minus 1. So this part is, what I get here is y hat of n minus 1. Okay. Now I can assume that, I will assume that for time n minus 1, y hat of n minus 1 was the correct decision. So x of n minus 1 is y hat of n minus 1. So I do this. Okay. Yeah, it is sliced or quantized, same thing, right? What's the difference? No, let's not worry about the implementation. That's not true also, right? I mean, if you, depending on how you clock it. In this case, it's just a comparator because we are already operating in the discrete time. There is nothing like in between two time instants, right? No, it didn't become, I assume that, so let's say I have a channel, I pass x of n through this channel, and the channel ends up giving me x of n plus alpha xn minus 1. So normally I would have fed this to a slicer, and the risk is because of intersymbol interference I will get the wrong decisions. Okay. So to get rid of intersymbol interference I have to get rid of this part of it. So one way of getting rid of that part is to simply subtract, if you don't know the value of x of n minus 1, sorry, you have a gain alpha and x of n minus 1. Okay. Now if the comparator is operating, if comparator basically slices whatever is here, and if the whole link is operating in an error free manner, then y hat of n should be equal to x of n. So I'll assume that for time n minus 1 that is true, that has happened to be true. So in that case I delay this by 1 bit and feed it back. So this assumes that this is the same as x n minus 1, and so far I am only considering binary data, but for any other data also you can do this kind of equalizer. So here what do we get? If all the decisions are right, then if you look at the signal here at the input to the slicer, the intersymbol interference is 0. Okay. So the two conditions, all the decisions have to be right, and this coefficient alpha that we use in feedback must be the same coefficient that appears in the transfer function of the channel. Well, yeah, for now we will assume that it has somehow adapted. Okay. Yeah, but you can use adaptation, the same LMS adaptation algorithm for this also, right? Because again, this is like right now it's a combination of, it's a weighted summation of two things. This one and this weighted by alpha. So you can adapt alpha using LMS algorithm. But for now, let's assume that magically you have the right number alpha from the channel characteristics. Okay. That's correct. That is just delaying. So essentially, see, I have intersymbol interference. That means that this, what I transmitted previously is affecting my current symbol, right? Now I already know what I transmitted previously because I've already received that bit. Assuming that the reception was right, I can subtract the intersymbol interference, right? So if I know what bit was sent, and if I know the channel characteristics, I know the contribution of intersymbol interference, and that's what I try to subtract off. Okay, that's what I'm trying to do here. Here the assumption is that, assumptions are that firstly the decisions are correct, and secondly feedback coefficient alpha matches the channel characteristics. So if it doesn't match it, then the cancellation will be imperfect. But let's say alpha is the alpha here is 0.5 and alpha 1 is 0.4. So it will cancel part of it but not completely. So are you convinced that this will equalize the channel? Are you also convinced that this does not amplify noise? See, the output here is digital, okay? This part is digital, it doesn't have any noise. So the noise here is simply the noise of this part, W of n. This is like an integrator. Why do you say it's an integrator? No, it's not an integrator. Right? So what happens if all x values are correct? You are saying that you don't need this, then it's a lossy integrator, not a lossless integrator. But you need the comparator to, see, the comparator is used because this value is still assumed to be analog. It has the value representing the digital signal plus noise. You have to convert it to a digital signal. So you need the comparator. No, how is that? Because see, in fact, let me not write x of n minus 1. Maybe, how should I write it? So let me make the notation clearer. So I have x of n. I have the channel transfer function, and the channel output y has the input plus ISI plus noise. Now the comparator output by definition is digital. So there is no noise added to this. The comparator output is digital. That's all. Okay. So if I feed this back with a coefficient alpha, there is no noise here either, isn't it? So when you have a comparator, it gets rid of noise. Maybe it has made the wrong decision because of noise, but the output of the comparator doesn't have any noise. Yeah. So actually, I'll come to that. So that's a good point. So I assumed all along that the decision was right. What happens if the decision is wrong? So maybe the next one also will be in error because of this, because you have subtracted the wrong value. So this kind of technique is prone to error propagation. If you make one error, you can make multiple errors. This is a nonlinear block. We can't characterize that with a transfer function. Okay, because for instance, let's take the value of alpha to be small. So is this a linear or a nonlinear block? How would you decide if it is linear or nonlinear? You have some block, okay, which you can analyze, simulate, do what you want. How would you determine whether it's linear or not? Output should be proportional to the input, or if you have two separate inputs, if you apply them together, the output should be the sum of the outputs of the separate inputs and so on. So let's say the output is either plus or minus 1, and let's for instance say that the alpha is small. In fact, I can take the trivial case of alpha being equal to 0, in which case I simply have a comparator which is definitely nonlinear. Similarly, for small values of alpha, if you increase the input, nothing happens to the output, right? So there is definitely a set of inputs for which, you go on increasing the input, nothing happens to the output. So it is nonlinear. So this part cannot be characterized with a transfer function. So only if it is linear time invariant can you characterize with the transfer function. So this type of an equalizer is known as a decision feedback equalizer. You make the decision, and based on the decision you feed back a certain signal to get rid of the ISI. In contrast to this, the kind of equalizer that we had been discussing so far, basically an FIR filter, is known as a feed forward equalizer, because there is no feedback in the signal path, right? You just delay the signals and all of them go through the forward path and you take a weighted summation. So FIR filter is commonly referred to as a feed forward equalizer. So this is a decision feedback equalizer. Firstly, it is based on the assumption of correct decisions. So that means that there can be error propagation. So once a particular value of y hat is not equal to y, you can't say, so I omitted the delay of z inverse here, you can't say what happens. Maybe that creates an error in the next decision as well, and which creates an error in the next decision and so on. So we'll analyze for a simple case what the effect is going to be. So it turns out this error propagation is certainly a possibility whenever you have feedback like this, because you make the wrong decision and then you are feeding back the wrong thing. Okay, instead of cancelling the ISI, now you are adding to the ISI, isn't it? So that's the problem. But it turns out in practice this is not a huge problem, and things do work well with the decision feedback equalizer. Okay. The second problem is, let's say we have a channel which is not xn plus alpha xn minus 1, but xn plus alpha xn plus 1. Can we use the same technique to cancel off the intersymbol interference? Can we or can we not? Why not? So to subtract the intersymbol interference for the nth, for time n, you need to know the value of the symbol at time n plus 1, and you don't know that. So that's why you can't use this to cancel the cancel precursor ISI. You can only cancel post-cursor ISI. Is this part clear? If you have xn plus alpha xn plus 1, the term I need to subtract at time n is alpha times xn plus 1. But that is the transmitted symbol for time n plus 1. I don't have that yet. Okay? So I can't really do a cancellation of precursor terms. If a current symbol affects future symbols, I can correct it. If a current symbol affects past symbols, I can't really correct it. Okay. Is this part clear? Huh? No, whatever it is. The xn plus 1 is transmitted after xn. So I am also assuming that I don't have access to this xn stream itself, right? I am doing it based on the decisions at the receiver. You are not convinced. No, if you can find a way of cancelling it, that will be great, but I think it's not possible. So the disadvantage seems to be that can only cancel post-cursor ISI, but the advantage is that, what is the advantage? No amplification of noise. So this is a huge advantage, the fact that high frequency noise is not amplified. So the decision feedback equalizer is a very widely used block in communication. Okay, especially particularly also because if you look at typical channels, they may have a few precursor terms but a lot of post-cursor terms. That's usually what happens. So by doing decision feedback equalization, you are getting rid of most of the ISI, which is due to post-cursor. To do precursor equalization, we need the feed-forward equalizer, the thing that we discussed before. We do need that. But if we have both the feed-forward equalizer and the decision feedback equalizer, we can let the decision feedback equalizer get rid of all of the post-cursor ISI. So you can design the feed-forward equalizer only to cancel the precursor ISI. The amount of precursor ISI is small. So the job that the feed-forward equalizer has to do is also small. So it doesn't have to boost as much, which means the amplification for high frequencies is also small. Okay. So what is the noise here at the input of the slicer? W of n. So that's all that is there to it. Let's take two cases. So I am sending yn equal to xn plus alpha xn minus 1 plus w of n through two kinds of equalizer. One is this decision feedback equalizer. Okay. So the signal here is x of n plus alpha x of n minus 1 minus y hat of n plus w of n. Now x is digital, y hat is digital. So the noise part here is only w of n. Okay. Let's think of a digital signal plus Gaussian random noise. Gaussian random noise can change the sign of the input to the slicer. That's how it creates bit errors, right? That's where you get all the Q function and the ERF function and all of that. Now let's make the kind of equalizer that we have been discussing so far, that is the feed-forward equalizer. Now here the channel is 1 plus alpha J inverse. What is the equalizer corresponding to this? Let's say zero forcing equalizer. 1 minus alpha J inverse. So essentially instead of this branch being in feedback, it will be here, isn't it? That's all. And this can go to the slicer and you get y hat of n. So this part is xn plus alpha x n minus 1 plus w of n. What is the signal that appears here? So the total signal that appears here is x of n and plus alpha x minus 1 gets cancelled out because of the contribution through this one. Okay. So what do we get? Minus alpha square x n minus 2. This we have seen many times so far. Plus the noise component because of that. What is that? Okay. Now let's say W is white noise. That is, it's not correlated from one time instant to another. So what is the noise variance that appears here? One plus alpha square times the sigma square of W. Okay. So the noise variance here is, let's say it's sigma W square. The noise variance here is sigma W square 1 plus alpha square if it is white noise. Is this clear? So you have more noise at the input of the equalizer. and the signal is also different. It can be smaller or larger than 1. In this case, if xn minus 1 is exactly equal to y hat, and if x is like plus minus 1, you will get 1. This is not y hat of n, this is y hat of n minus 1. Okay, so this is a very simple case, easy to understand. It illustrates that in this case you have noise amplification. This 1 plus alpha square is the noise amplification, and that comes out because of high frequency boosting. Whereas in case of DFE, you don't have it. Is it okay? So everyone is convinced that DFE, this is shortened to DFE. DFE does equalization without amplifying noise. Of course, it does equalization only for post-cursor ISI. You can't do it for precursor ISI. Now, what happens if you have a more complicated channel, x of n plus alpha 1 x n minus 1, alpha 2 x n minus 2, and so on? We have to basically extend the same thing. So, let's say the channel response was xn. So, as many as you want. Now, essentially we have an estimate of xn minus 1, xn minus 2, xn minus 3 from the previous symbol, the symbol previous to that and so on. So, we assume that they are equal to, the decisions that we made are equal to the transmitted symbols and feedback all of them. So, if you have 3 taps, you need 3 delays. In all these diagrams, it's assumed that there is no delay through the slicer. So, we have not come to the implementation yet. In the implementation, there will be a delay, but maybe part of it can be absorbed in the inverse. We delay the decisions by as many symbols as we want, and then feedback all of them. So, this alpha 1, alpha 2, alpha 3, the coefficients in the feedback of the decision feedback equalizer should be the same as intersymbol interference taps in the channel. Okay. So, in reality, they will be slightly different, so the cancellation will be imperfect. So, in this case, if you have the taps to be you have the feedback fractions to be the same as the taps of the channel, then the ISI is cancelled completely. So, what is this part of the filter? If you look at this, with this as the input and this as the output, what is that? Where do you see that in the system? I mean, this is the equalizer, but that transfer function, that is the channel, right? With the exception of the cursor. So, it's the same as the channel. So, you have the post-cursor part of the channel. You have a response h of z, and you group everything that has powers of minus 1 or less, and that is this. Okay. So, you take that and put it in feedback around a comparator, and you have your decision feedback equalizer. So, if alpha 1, alpha 2, alpha 3 matched the channel exactly, so let's say the channel had 3 taps, and you have 3 taps in the decision feedback equalizer of the right values, then between the input and output, it looks like there is no ISI, right? So, it's not a linear time invariant, it's not a linear system, so we can't really characterize it by a transfer function, but we do know that if we send a pulse like this, we get only one non-zero pulse, because all the other parts will be cancelled off by the decision feedback equalizer. So, I am not calling this the impulse response, because it's not a linear time invariant system or the transfer function, but this is what you get. Yeah. Yeah, I mean, it has to be correct at some point. So, we will see how the probability of error gets modified, right? There is some probability of error. So, let's see what happens to that. Okay, that's the next thing that we will see. So, it's not necessary that, see, you make one error, then the next one can be in error and the next one can also be right. That's also possible, right? Because of the way the noise is, it's possible that the next one is also right. So, it can come out of that state. It's not as though if the first bit is in error, every further bit is in error. That's not the case. There is some probability associated with the error of following bits. Now, it can come out of a state where you make error in one bit and then after that it's fine. And anyway, I mean, if it doesn't work for that, it would not be a useful system, because of noise, whatever you do, there is going to be some probability of error. Okay, so it has to come out of that, and I'll show you what happens to the probability of error. In fact, we can look at that next. I think this is all I had to. So essentially, the feedback part. See this. So this part. This looks like an IR filter. The only difference is you have a comparator in the forward path. If I didn't have the comparator, if I replace that with a path like this, that would make an IIR filter whose transfer function was 1 by 1 minus something something. Okay, alpha 1 J inverse and alpha 2 J inverse square and so on. So it is, you can also think of it as being an IR filter with a comparator in the feedback path. Okay. No, this is digital feedback. That's the assumption here. Okay. So in circuit implementation it may get added, but digital, I mean, if you are, let's say you create it out of some saturating block, the noise at the saturation levels is small. So that's a reasonable assumption even in practice. But the key here is that it is digital feedback. So that is the key difference between these two. So if you look at the first diagram, the output has only W of n, whereas here you have the noise added plus, I mean, some linear combination, W of n alpha W of n minus 1. So here the feedback is digital, so it doesn't add any noise. So it is up to you to make sure that the digital feedback in fact has low noise, but that's also easy to ensure. That part is not difficult. Okay. The hardest part turns out to be, like, because it's a feedback system, it can become unstable, or in this case we don't call it instability, but see, in practice there is a delay through the comparator, and if you implement the Z inverse to a flip-flop, there is another extra delay, as you saw in the first assignment. The waveforms don't look like anything as though the clock is synchronized, I mean data is synchronized with clock, right? There is a big difference between when the data changes and the clock changes. So there is excess delay through everything, and you realize the coefficient, there is a delay through that also. After all, it's an amplifier. Okay. So all of these excess delays can add up to a lot. So if you want to get the value of the symbol at time n correctly, the value at time n minus 1 must be fed back in time. If it comes too late, you are not subtracting the right value. So that is the hardest part in implementing a decision feedback equalizer, whether it's digital implementation or analog implementation. Okay, so let's see what happens to the probability of error. Again, we'll take a dummy simple channel like with a one tap ISI. So this is the input to our decision feedback equalizer, and W is the noise. Again, it's additive white Gaussian noise from the channel. So Y hat is fed back with a delay. Now let's say the symbols X are plus minus 1, and the decisions Y hat also of course are plus minus 1. So let's say there is a certain probability of error. In this case, the probability of error is defined as the probability of Y hat of n not being equal to X of n. Okay. I mean, for any particular time, the Y hat is not equal to X, that is error by definition. So how do you find out the cumulative probability of error? So I want to know what the total probability of error is, this PE, in terms of this noise and other things. How would I do that? Yeah, that's correct. So essentially I have to look at the value here, whatever the signal value is, the variance of noise. The variance of noise is clear. We know that it has no other component of noise. It is sigma W square. Okay. I need to know the variance of the signal, I need to know the signal, the variance of noise, take the ratio of the two and take the Q function, that's the probability of error. Now the feedback can be correct or the feedback can be wrong. Okay. So you have to take that also into account, isn't it? So let's assume that the feedback is correct, that is the feedback value for the previous symbol. So let's say we are evaluating this for time n. So let's say Y hat of n minus 1 is X of n minus 1. Okay. So what is the probability of error in that case? What is the value that you get here? I mean, not the noise component, the signal part of it. X of n. Okay. Which is either plus or minus 1. So what's the variance of noise? What's the standard deviation of noise? So let's firstly, the feedback is correct. So the signal is plus or minus 1. What is the noise? Noise variance or noise standard deviation? Sigma W. I say noise equal to sigma W, it's assumed that it's the RMS value. Okay. What's the probability of error? What is it? I mean, in terms of Q functions or ERFC or what? You know what a Q function is? So it is Q of 1 by sigma W. Okay. So if it is 1 with a probability of Q of 1 by sigma W, it can become minus 1. If it's minus 1 with a probability of Q of 1 by sigma W, it becomes plus 1. So if you have, let me just explain quickly what Q function is. The signal is supposed to be either plus 1 or minus 1. Okay. Now to the signal we have added white Gaussian noise. So the signal cannot be represented as either plus or minus 1, we have to represent it as a probability distribution function. And the probability density function looks like this. So this is essentially the probability of the signal 1 plus the noise being a certain value. And it is less than 0 for this part. The area of this is Q of 1 by sigma. Okay. Now if you go to the minus 1 case, because it's a symmetrical distribution, the probability of it being greater than 0 is again Q of 1 by sigma. So whether it's plus 1 or minus 1, the probability of error is the same in this case. Okay. So the total probability of error is Q of 1 by sigma. Is this clear? Q is just this area, right? It can be expressed in terms of error functions, ERF, ERFC, whatever you want. Q of, let's say, so let me not write this, it's some integral of the, so this is the probability of error when the feedback decision was correct. The secondly, feedback is incorrect. That means y hat of n minus 1 is not the same as x of n minus 1. So what is the signal? What is the noise? 1 minus alpha? 1 minus 2 alpha. Is it 1 minus 2 alpha always? I mean, what are the possible values when the feedback value is wrong? It's either 1 plus 2 alpha or 1 minus 2 alpha, right? So it could be 1 plus 2 alpha or 1 minus 2 alpha. Is this part clear? Or no? The x of n plus alpha xn minus 1 can have values of either 1 minus alpha or 1 plus alpha. So x has values of plus minus 1. So let's say x is 1 and xn minus 1 is either plus 1 or minus 1. So the values that are possible are 1 minus alpha, 1 plus alpha, minus 1 minus alpha, minus 1 plus alpha. Okay. And now you have the feedback in the wrong direction. So instead of taking you close to 1, it is actually taking you away from 1. In one case it increases the signal, in the other case it decreases the signal. And then what is the noise? Same, sigma w, because the feedback component has no noise. So it is sigma w. What's the probability of error? No, this is just this, what is it called, chain rule or something, right? You have a whole number of dependent events and you multiply the probabilities together. So what is the probability of error if this is the case? So if this is the case, it is Q of 1 plus 2 alpha by sigma w. What if this is the case? And what is the total probability of error? So these two are equally likely cases, so it is this plus this divided by 2. Anyway, we are running out of time. Now you complete so we have all the piece parts of the calculation. So you complete the calculation for the probability of error. Okay, when we meet, I think next week. Yeah. So that will tell you how much the probability of error is enhanced because of the possibility of wrong decision. You are asking like how it will come out of it. So essentially we have now a cumulative probability of error, including the fact that the feedback is possibly wrong. Okay, so you can do that calculation and see how it affects. And you are also asking, it's a relative thing where you put the cursor. That also comes out of this. Okay. Any questions?